once you have the written down procedure that you're going to be applying to analyzing this case, you can actually test that on similar cases. You could actually say, these are the 17 cases that are similar that I can actually test that procedure on and see if my procedure delivers the right outcome. And that means that I can get a statistical assessment of the probability of this procedure delivering the expected outcome based on relatively few data points. So just like the 19 cases, if we had 19 cases, I could run that through, and in 16 of the 19 cases, it gave a good verdict. It ended up with predicting the verdict that we also had, and now the confidence of this system is actually very high, although it was formally trained on only 19 cases that are even quite diverse. They could be quite different in their structure. So what that means is that since you're not necessarily consuming massive amounts of data to generate the procedure, you have that data available subsequently to validate the procedure, which makes symbolic AI a very good fit in situations where you have little or even no data.
So, hi everyone, and welcome to the AI and Digital Transformation podcast brought to you by GMSC Consulting. We are your hosts, Angelique and Gabriele. In this podcast, you will learn how you can integrate all sorts of AI and digital transformation solutions into your business. So for today, our guest is, hailing all the way from Denmark, Casper Wilstrup, the CEO of Abzu. So I'm just reading it off from LinkedIn's short bio. So Abzu builds AI that finds transparent and understandable answers to the world's unanswered questions. It sounds very epic, doesn't it, Gabriele?
Yeah, it does sound interesting, and the subject, it's very interesting indeed. It's almost like what they do at Abzu is almost a jump into the past, but it's actually a jump into the future. So it's really interesting to discuss it. And so let's start.
Yeah, so welcome, Casper, to our podcast.
Thank you, and thank you very much for having me here today.
So before we begin to dive into the world of Abzu, we just want you to share like a few words about yourself. Who is Casper? I mean, I have an idea who Casper is, but the world doesn't know.
That's great. Yeah, so I have a background in physics a long time ago. Back in the 90s, I wanted to be a physicist, but I ended up getting a very strong interest in high-performance computing and supercomputing, and later on AI. And that brought me out of physics and into doing various startup companies and working to try to solve data-intensive problems using different technologies, mainly involving a lot of computing power. So gradually that became known as AI, and it's fair to say that I worked in that field for 25, nearly 30 years by now. Sometimes as a founder, sometimes as a consultant for several years, also on the venture capital side, and now again for the last 6 years as a founder of a very AI research-focused company.
So let's go right to the gist. So your AI company, the one you contributed to found, Abzu, is involved in, let's say, not common approach to AI nowadays, even though that's how AI started somehow, which is symbolic AI. Could you give a brief introduction of what symbolic AI, and more importantly, why do you think it's important for the businesses out there?
So in terms of what symbolic AI is, actually when the field of artificial intelligence was brand new, on the day the actual term artificial intelligence was coined by a gentleman called John McCarthy back in the early 50s, what people meant when they talked about artificial intelligence was what we today call symbolic artificial intelligence. Symbolic artificial intelligence is about mimicking the rational human thinking process. It's things such as math and statistics and logic, things that we tend to learn in school and that are hard to do but which we can do if we are appropriately trained. The feeling back then was that since we had just invented computers, the next natural step would be to invent computers that could actually do rational analysis in a way that's very similar to the way humans work. But that turned out to be very, very difficult. So for several periods between the 50s and the late 80s, different ideas about how to do AI, and here symbolic AI, was brought forth, and they worked moderately well, but never really to the level where they became fully useful. And that's what led to this sequence of AI summers and winters. Then in the late 80s, another approach to artificial intelligence came to the foreground, an approach that we in the field called sub-symbolic AI, but which is best understood as neural networks. A neural network and a bunch of similar approaches are actually trying to tackle the problem in a completely different way, in a much more pattern recognition oriented way, where the AIs are really good at recognizing patterns in enormous amounts of data and then replicate structures found in that patterns and predictions. So that turned out to be the leading approach to artificial intelligence from the late 80s, early 90s, and then on to quite recently. And that completely pushed the idea of building AI that can deliver rational explanations to the background. And we started to become acquainted with things such as hallucination problems in artificial intelligence, or the Blackbox problem in artificial intelligence. Here referring to the idea that if you ask the AI to answer a question, it may answer, but it doesn't give you any indication of how it arrived at that answer. So that's a problem with sub-symbolic AI, or the kind of AI that is focused around neural networks, that remains unresolved in that approach to artificial intelligence. And it has given AI the reputation of being hard to understand and black boxy and dangerous to use in many situations. But actually, all those considerations apply to sub-symbolic AI, whereas the good old-fashioned AI, the symbolic AI methodology, does not really suffer from those problems because it delivers its explanations. It delivers clear answers to how it arrives at its decisions or recommendations or predictions. However, it turned out that it was quite difficult to build symbolic AI, and that's why I founded Abzu, because for many years I had an idea about a new and different approach to actually tackle the problem of symbolic AI. So back in 2018, I put together a group of high-performance computing experts and AI researchers that I've gotten to know over the years, and I established Abzu to see if we could realize this new kind of AI that does not suffer from these black box problems in that sub-symbolic AI has. And that turned out to be possible. So after some years, we published and patented an algorithm that now is leading the pack of symbolic AI algorithms out there. And we believe that by bringing that more to the foreground, utilizing that in many of the use cases where it's difficult to use AI today, and maybe combining it with the sub-symbolic methods, we can overcome all of those problems that have come to be central in the discussion around artificial intelligence.
I think the symbolic AI approach is very effective when you have to cross that bridge that goes from research to actually business, because you have to trust the result when you want to use AI for any kind of business application. And in order to trust, usually we humans, we need to understand, and that's the big problem with artificial AI. And also as in the daily practice, we see that there's a lot of skepticism from businesses, especially from businesses that have been out there for a while and maybe they're not so big. And they look at it like something very promising, but something that they do not understand, and hence they're scared of it, despite their understanding of the potential. And symbolic AI can actually cross the bridge. It's something that I've also been often interested in, and I actually found in several of the papers published by Abzu, like some of my thoughts. So I really enjoyed reading them. And I think one of the best part that I think I found, and that is the cornerstone that bridges the two words, symbolic and sub-symbolic, or neural networks and rule-based in a way, AI, is the brain, let's say, biomimetic approach, let's say. So the idea that the two sides of AI are also included in how our brain works, meaning that sub-symbolic is basically the perceptive AI. I think you used this word in the paper. I don't remember exactly, but and so like our visual cortex, our temporal lobe, our audio sensory cortex, and so on. Those are all sub-symbolic neural networks in our brain that translate highly dimensional inputs like audio or visual into some archetypes, some symbols that we can understand. But then what we do with that understanding, how we put it together, how we learn from experience, that's symbolic AI.
That is exactly right. I use this analogy quite often that it's the human brain has really two capabilities that work in conjunction. And one is this pattern recognition, perception, sensory. It's a little broader than that because it actually also includes interpretation and generation of language, are all done by a sub-symbolic process. And when you think about like your own conscious processes, you can actually recognize the sub-symbolic processes that they don't require any mental energy on your side. You recognize a buzz in a picture or recognize speech, understand what is being said without applying any conscious energy. But then when you want to try to solve a problem or think about how to act in the world based on reason, then you need to apply mental energy. And the analogy is actually pretty much one-to-one, that the sub-symbolic processes in the brain are those that we feel that we do intuitively without applying mental energy, whereas the symbolic processes in the brain are those where we have to concentrate, we have to focus, and we have to use skills that we learned in school or elsewhere to actually solve these problems. So for a human being, it's actually quite familiar to switch back and forth between sub-symbolic being and symbolic reasoning or rational thought. So most of us actually know what we're talking about here. And that also means that we can relatively easily get a grasp of what it is that we can do if we do symbolic reasoning, because most people are able to do that as well. So if you allow me to give you an example of how a process like that works, let's say that I ask for the number of red cars in a city in, let's say, in Copenhagen, where I live. Then most people can actually solve that problem. They don't necessarily know the answer, but they're able to write down a procedure to arrive at the answer. And that's a very formal procedure. They will write something like, first we take the number of people in Copenhagen, and then I multiply that with the fraction of cars that are red, and whatever, the number of cars in per capita, and then the number of cars that are red. So we can write down a procedure that can actually be used to arrive at that answer. But we do that with no data. Like we just generate, through some magic process, we generate this way of arriving at the answer. And now when you have that procedure, it's important to realize that procedure can actually be tested. I can test that on the actual number of people who, on the actual number of people and fraction of red cars and subsequent number of cars. So I can get a quick estimate and very accurate estimate of how good that procedure is at answering the question. And that's very unique to symbolic AI, is that we can actually write down a procedure like that we can then actually test on real world observations, which means that we get this confidence. This is how we're answering the question, and this is how good we are at answering the question. That are things that you can get out of the symbolic AI that you can never get out of the sub-symbolic approaches.
Yeah. I mean, I listened to one of your previous interviews, and you mentioned that your brother had this analogy of symbolic AI wherein like in one Star Trek episode. I think all the sci-fi people would love this. There's this Star Trek episode where the Enterprise is being duplicated or something like that, and then you try to understand, like, what could happen, or maybe you could elaborate on that, because it's something that also somehow describes symbolic AI.
Yeah, so that moves us into talk about how we actually solve the problem of symbolic AI. Because the reason that the McCarthy and later era symbolic AI approaches did not succeed is that it's a very, very difficult problem to actually solve. You're searching through a solution space that is actually infinite. If you try to write down all the possible ways you could arrive at the number of red cars in Copenhagen, then you could continue writing. Some of them are obviously silly, like starting with the number of red flowers in the meadows in Fælledparken or something like that. But if you know nothing about the world and you're just starting off with, I just want to look at them all, then the number of different explanations that you need to consider is infinite. And that means that you have to have some clever way of pruning that infinite space, some way to actually get to the bottom of which theories or which ideas to solve the problem are more likely to be true than others. So you're searching an infinite space. And the core realization that I had, and that led me to found Abzu back in the days, is that problem is very akin to a problem that is often solved in quantum field theory. So quantum field theory is a physical problem where you're studying a number of quantum particles interacting with each other in space-time. And the problem here, as demonstrated by Feynman, can actually be understood as studying an infinite number of possible world lines that these particles could take. And therefore, supercomputers have been developed that are good at studying that. And the idea that was the founding idea for Abzu was that those same methodologies, I won't really bore you with all the mathematical details here, but those same methodologies that are used to study this infinite number of world lines for particles can also be used to study the infinite number of explanations that could be written down to arrive at this procedure, the red cars in Copenhagen procedure. And that's where my younger brother brought the analogy. So it's kind of like in this Star Trek episode. I'm not a Trekkie myself, actually. I do like science fiction, but not that much Star Trek. Don't tell my brother. Oh, now I did. Bummer. And here you have the same idea. Like the Enterprise gets duplicated in like a gazillion different spaceships, and then you can kind of look at them all and imagine here that you're looking for the one with a red dot, or the original Enterprise, in this cloud of Enterprise spaceships. And that's very akin to how we actually solve that in our core technology, which, by the way, is called the QLattice, where the Q and lattice here actually alludes to its origin in quantum lattice gauge simulations, which is the formal name of the methodology it's inspired by.
That's great. Right.
Yeah. Q is also a godlike character in Star Trek. So
Yeah.
it's regarded. Yeah. So I think it's best if we try to give a concrete example. We can make it up just to give an idea to the listener how it works. So especially in nowadays world where 9 out of 10 or 99 out of 10 AI solutions that you hear are about LLMs.
99 out of 100, you mean?
Yeah, not 99 out of 100 are about LLMs. I think we could try to elaborate a bit on that. So, like, I think we could imagine a problem where we want to use AI to analyze some text, for example, some legal text, okay?
Okay.
And we want to use an LLM to extract some relevant information, some legal concepts or topics from the text, from documents. But then our task is to decide whether we could, for example, proceed with like if there's a case, a legal case or not, given the evidence that is analyzed by the AI.
Mm-hmm.
Okay, so it's a very hard problem, I know, but
No, it's spot on.
but I think it could be a good example. So like let's try to picture this example, and how would you see like your technology work in this context?
So I'll add a couple of extra assumptions. So let's assume that we're working in, say, a case law situation. So in order to assess the probability of a certain outcome in a legal context, you need to consider various equivalent cases, like say in the UK legal system. So here the setting is that you try to determine the procedure that will be used to determine the outcome of this legal cause. Just for argument's sake, let's assume it's a criminal case. So we're looking at what will be the actual verdict in a criminal case. So in order to use so if you were to set a large language model to work on that problem, it would analyze all the text content of all relevant cases, and then it would say, based on what I read, I think that we will likely get this verdict. And that's it. Right? It just based on the readings here, it just constructs a prediction about whether or not you'll get a certain outcome in a case, in a criminal case of a certain. And the problem of course is that leaves the human with no way of determining whether they trust that. What is it based on? Is this something that's credible? Is it going to be shot down in certain ways when I actually start to make that argument? How will I even make the argument? Because the AI just generated like a verdict. Of course, you could ask it to try to generate like the procedure as well, how you should argue your case, but it would essentially just hallucinate that. It would just construct some kind of believable narrative. So it wouldn't really be a system that I would rely on if I were defending a case in a court. So, but into symbolic AI, the symbolic AI would essentially do the same thing, read the same cases, but it would then construct a procedure which would then it would actually be the equivalent of a law text. It would say that I assume that this is the way this is going to be analyzed, and that is why I assume we'll come up with this verdict. And that means that now the lawyer can look at this procedure that is stipulated and this logical flow that is stipulated and say, I believe this or I don't believe it. So the lawyer can assess whether this is plausible. They could also choose to use this to rethink, like how I'm actually going to do this case. And ultimately, they could also do the case by following like the same procedure that the AI stipulated. So ultimately, the point again here is that the explanation or the step-by-step procedure is more important than the AI's assessment of what will be the verdict, because it allows a human to use this for something in practice.
But wouldn't you still use a language model to extract, for example, topics from the document or in general features from the legal documents that have been analyzed? Because otherwise, I would assume the symbolic AI problem would be intractable.
Indeed. So, but if we take one step back, actually, you could do that without analyzing any actual cases. The AI could, just like with the red cars in Copenhagen. I don't have any specific expertise in calculating numbers of cars in cities, but as a human, I could still bring up a procedure. And in the same way, even if I knew nothing about case law, I could actually bring up a procedure that just probably be wrong. It would be a wrong procedure. But that's because I don't have sufficient prior knowledge about the domain. So for a symbolic AI to work well, it needs to somehow filter the topical information that is available by it. So in a certain sense, a symbolic AI is a domain expert in its own right. And the more material it has to work with, the more of a domain expert it is in a specific field. But the paradigm itself, the symbolic paradigm itself, does not really rely on domain expertise. It's just an additional quality for the procedures that it proposes.
So I wanted to ask, like, how good should the data quality be to be able to make this sound judgment? Because I think that should be the case, right?
Well, so going back to once you have a procedure, once you have the written down procedure that you're going to be applying to analyzing this case, you can actually test that on similar cases. You could actually say, so these are the 17 cases that are similar that I can actually test that procedure on and see if my procedure delivers the right outcome. And that means that I can get a statistical assessment of the probability of this procedure delivering the expected outcome based on relatively few data points. So just like the 19 cases, if we had 19 cases, I could run that through, and in 16 of the 19 cases, it gave a good verdict. It ended up with predicting the verdict that we also had, and now the confidence of this system is actually very high, although it was formally trained on only 19 cases that are even quite diverse. They could be quite different in their structure. So what that means is that since you're not necessarily consuming massive amounts of data to generate the procedure, you have that data available subsequently to validate the procedure, which makes symbolic AI a very good fit in situations where you have little or even no data. Like in the extreme, you could use this if you have no data, then just don't get any kind of confidence intervals. But in the case where you have like just 19 equivalent cases to study, then that would be that would be adequate to get a good assessment of how likely this model is to predict or to yield the correct prediction of verdict.
Yeah, that's a massive difference between like existing LLMs compared to symbolic AI, the amount of data.
I think from the amount of data perspective, symbolic AI, it's like, especially in the way that Abzu developed it, which is basically a search in the functional space of function compositions. And it's a highly regularized and biased procedure. So it's like using very simple function to learn from the data, which usually yields a low accuracy, but combined with the function composition and the search space, it actually can be a good combo of flexibility and simple function that can be learned even when the data is very small, with the data set that's very small. And but from this perspective, my question is, how similar is your approach to causal inference?
So ultimately, causal inference is impossible without intervention. So there's a fundamental principle in causal inference that we just have to respect since we live in the real world, and that is if you've studied some relationship between A and B, then in its own right you can observe that as long as you want without ever getting any picture about whether A causes B or B causes A. The only way you can actually determine whether it's one way or the other way, whether the arrow of causality points one way or the other way, is by intervening. It's like the idea of an intervention study, or the fundamental idea of experimental science, is you have to go in and turn off A and see if B still occurs, then B caused A, and but if B also stops occurring, then A caused B. And that's the idea of an intervention study. So you can't really be certain about the causal direction. Causal inference, at least the flavor of causal inference that I believe in, relies on another principle to still assess causality. And that principle has to do with what in science is called Occam's razor. So the idea is that if you observed a set of things that work together, like A, B, and C are correlated with Y, and you want to understand whether A, B, and C are correlated with Y, then the number of inputs that are required to accurately predict Y is a strong indicator about whether the model is causal. So to just give you an example here, if you have a mutation in your gene set that causes a disease, then it's very, very likely that you will be able to find a model where there's like a one-to-one relationship, right? The gene causes the disease. So you will find a simple model between the gene and the disease. Whereas if the disease is the cause of a lot of bad measurements in your blood, like a serum measurement in your blood will show all sorts of things being off the record, off the charts, then here you are actually seeing the disease being correlated with a very large set of other variables, which in this case would indicate that the disease was the cause of the serum measurements. So actually down-regulating. So let's take an example from medical science. Like if you have an infection of any kind, you have a high CRP level, C-reactive protein. But regulating your CRP level down will not cure the disease because it's a symptom of the disease. It is not a cause of the disease. But at the same time, you will also see a very large set of other things out of normal in a measurement on the blood sample. So you would actually know that this is highly likely that the causal arrow goes from disease to the measurement. So the principle here, it's been mathematically formalized as something called archaic information criterion, but more popularly thought of as Occam's razor. We're essentially relying on that if things are causal, they must also be simple, because causality requires interaction, and therefore it's highly unlikely that a long sequence of events happen in a certain way. So if you can make a simple explanation, it's simply more likely that it's causal. And that also means that if our symbolic algorithm can yield a procedure that is very good at predicting an outcome, then you can also, with a high confidence, believe that the inputs to that procedure are causal of the output. Whereas if it's not very good at predicting the outcome, maybe it's just a rough estimate, then it's more likely that it's actually not causal.
Yeah, well, for sure, like causal graphs must be simple to be accurate. Like, as you said, Occam razor, that's a good principle in general. So definitely, I think the difference is that in general...
But only if you apply it that way.
Yeah, I mean, I think the in general difference maybe is that symbolic AI doesn't need to distinguish between causes and effect, as long as the explanation is simple. So that's an advantage, and a disadvantage. It depends what you're looking for, of course. It really depends on the
yeah, but you can certainly use it to identify these causal situations. So an example, if I fit a symbolic model to predict the pixels on a picture of a bus, then it won't work. You cannot predict the color of an individual picture, a pixel on a picture, from the fact that there's a bus on it, because the bus caused the pixels. It's not the other way around. The pixels didn't cause the bus. So you can take it as a very strong evidence that the direction is causal. If there exists a simple model, then it very likely is a causal model.
Yeah, I mean, but like you could see, like every time you see a bus in the picture, you know that somewhere it's passing a bus because maybe there's an IP camera connected. So the thing is that causal AI causal inference would require to understand what's the source of the causal mechanism, the bus or the camera. The symbolic AI, if you want to explain when, I don't know, the bar of the parking has to lift, that doesn't need really to distinguish between two events that are strongly correlated. It will just choose one because it doesn't need to choose both. And you realize this both would be an overkill for all algorithms. It will just choose one that is strongly correlated in a way with a simple law. So it's actually cool. And it's actually a cool approach that I think it can help explain a lot of different situations, especially when the explanation is simple. Because one of the doubts that I actually had while reading your papers is, what if the law that we're trying to extract is not simple? Like, because yes, when you can explain something using like rules, like if and else rules, or like composition of simple formulas like addition, subtraction, division, and so on, exponentials, everything, it's simple. But like if you were trying to explain, for example, something that is not regulated by simple law, how would the system fare? Like,
what kind of example?
Like, for example, I don't know. Like, you want to, I don't know, any law that is not simple, like, I don't know, what can we say? Like, I'm thinking about something simple. Do you have any idea of a simple example that is not the good fit for this approach?
For symbolic AI.
Not for symbolic AI in general, but for the technology that we have now. Because in general, if in your toolbox of function you have the right function, that symbolic AI works very well. My question is, when the problem you're trying to model is not well fit by any of your toolbox, what will happen?
Yeah. So maybe a good point to bring up now is that the paper you have is explains the QLattice algorithm in context of mathematical operators. So here we're looking for symbolic explanations that can be expressed as mathematical formula. But the QLattice algorithm is not limited to search for mathematical expressions. It can equally well search for logical expressions or Bayesian expressions, or for any kind of formal system. So it's very often useful to try to use it to search for mathematical relationships, because they have some core advantages. But there's nothing inherent in the QLattice approach that means that it has to be mathematical operators. So when we apply it inside of our full-scale system, it will also be able to come up with logical explanations or step-by-step procedural explanations. But in all of those cases, it still is true enough that if there are formal principles that the system does not have available, then it cannot express procedures that uses those formal principles. So we are limited to. That's why symbolic AI is similar. That's why I kept saying this thing with what we learn in school, right? Because if there's a formal language that you have not learned in school, let's say predicate logic, if you don't know what that is, you cannot express problems that can only be expressed as predicate logic. So there are certainly types of formal systems that our symbolic AI is not able to use, and that would then mean that we wouldn't be able to capture formal procedures that could be expressed in that language. I would say it's very rare, because actually there's a large overlap. If you can express it in logic, you can actually also express it in math. If you can express it in math, then you can actually express anything that can be expressed in Bayesian in Bayesian priors and posteriors, like Bayes rules, chains. So it's not really a problem that we come across, at least as long as we're looking at the causal situations. Because actually, I think what made you hesitate before is it is very, very difficult to come up with a relationship in nature that actually exists in nature, where the causality is that way, where the rule is not also simple. It is super difficult, because then we're most likely talking about more than one thing, or you're talking about something where causality is confusing or goes wrong. And we've seen this again and again, that people have come to us with a problem of some kind, where they fitted a Blackbox model that was fairly accurate, and then this is just too complicated. You can't find a simple explanation here, because this is a complicated thing, and we don't believe that that's possible. And then we analyzed it, and voila, found a simple explanation that was just as good as the Blackbox model they had predicted. So it was just because they didn't know that there was a simple explanation, but that does not mean that there isn't one.
Okay, now that brings me to my next question, because I wanted to understand, are people familiar with what Abzu does? Because symbolic AI is not that popular compared to, let's say, LLM, obviously. So yeah, how do people approach you? Do they need to have substantial amount of knowledge on AI to be able to work with you and use QLattice, or not?
No. So we love working with situations where people really care about the why. That's where. So when people approach us with a problem that can be in fraud detection, in credit scoring, in risk assessments in a financial setting, or in logistics, where you want to understand the dynamics of your transport network, be that an airport or a railway, or in manufacturing, where you want to understand why your machinery doesn't deliver, why it has instability, or in maintenance, where you want to understand why things break down and when. In all of those situations, what is essential is that you actually care about this why. You care about the procedure. why does the windmill break? Why does this ripple effects in my railway network behave the way it is? Why do these patients not respond well to a drug? Why is this a good or a bad investment? Why is this likely to be a customer worthy of credit? And so on. You want the why. And in all of those cases, language models are off the table. You typically have somebody who wants you to answer that why question, be a customer or a manufacturer or a patient or a doctor or a clinical researcher, what that is. So the situation that people who approach us with those kind of questions, like that's just a perfect fit. And what we shy away from is when you're only interested in like the prediction itself. That's where you might as well use Blackbox artificial intelligence. If you genuinely only care about whether this person will buy a bottle of milk or not, then why use a symbolic procedure to determine what decides whether you buy milk or not? But I would say the use cases are more widespread than people immediately think. So I think that there's a massive future for symbolic AI. I think as we are rolling out this technology and now also combining it with sub-symbolic AI so that we can actually make it easier to use, I actually think this is an approach that has potential to take a very, very large fraction of the market.
So we'll leave the question in a dual space. So one version is, what are the problems you have now with your approach, or if you prefer, what's coming next?
Yeah. So the interesting challenge with symbolic AI is that since it does not encapsulate the perceptive part, we're not doing the perceptive part. It's not really good at, say, interpreting what a user asks it for, or interpreting visual data, all those things that are like humans like to interact with systems. So just take an example. Most people find it very easy to chat with a large language model because we just write in our own language and it does its interpretation. But that here, the language model is leveraging its force, right? It's a language model and it's good at something that is sub-symbolic in nature. The symbolic artificial intelligence is not good at that. It's not good at talking to humans or interpreting fuzzy words. Historically, also for Abzu, while we've been like operating commercially, it has been, the bigger problem has been that you have to learn how to use it and you have to apply it right. And the big potential that we're working on, starting to roll out to some customers today, is fusing the two. So actually, just like the human brain is good at both, we can build AI that is good at both. So you can interact with it as easily as you can with ChatGPT or a similar model, but it doesn't use ChatGPT or the language model to answer the question. It just uses the language model to transfer the question onto the symbolic AI that then delivers a good procedure to answer the question, including some statistics on how accurate it is, and then maybe pass it back to the language model that can then explain it to the human. So we're seeing this perfect match between the sub-symbolic capabilities of language models and the symbolic capabilities of our AI, fusing into a system that can really scale well. You just bring this out to virtually anybody who has these kind of problems where want a formal procedure, and now they can actually use it themselves without understanding the intricacies of applying symbolic artificial intelligence.
And by the way, I was thinking that it would be nice to combine this. I don't know if you already had the chance, but to combine symbolic AI and causal methods. Like I would like to use Faye and QLattice to solve an uplift model problem. I think it would be nice.
Yeah,
it would be very interesting.
Yeah, I think that there's something, certainly a potential there, but it's actually not something I, at least personally, have explored.
Yeah.
I can't say for sure for all the other AI nerds in this company. Could very well be.
Yeah, because you could like whenever you can use some kind of meta learner, and you could think of these also. That's one possible example, and you can apply it to several causal problems. And since their approach, the symbolic approach, requires less data, you can actually get a much higher quality result, combining the best of the two worlds. So That would be really interesting. And so, for the ones of us who would like to give it a try, how much of this solution is open source or available, and what's your business model, basically? Like, what if there's anything open source, what do you provide that's beyond it?
So the QLattice algorithm as such is quite broad, and the fine library is one that we provide free of charge for non-commercial use. So if you're a researcher or you just want to try it out, then you can actually download and install Fine on your machine, and that includes a mini version of the QLattice. So right on your own machine, you can actually run this symbolic AI, but limited to mathematical functions. So what you'll end up with is a system that can locally find mathematical formulas that can capture what happens in your data, and everybody are just welcome to try that. So our license terms say that if you want to use that inside of a commercial product or for commercial purposes otherwise, then you have to buy a license to use the QLattice technology. But to get started, it's just a pip install, and then you're up and running with the Fine library. The QLattice algorithm can do much more than that. If we run it on like our systems and combine it with a lot of the other components that we have, including the language models, then we can solve much more complicated and large-scale problems, and also explore other symbolic languages than just mathematics, including programmatic procedures. So including like step-by-step execution of code to arrive at a way to answer a problem. So here we're getting closer to code generation, actually custom code generation that solves the problem. And these are things that we do in collaboration with partners. So either we work directly with end customers who integrate our capabilities to do this into their systems, or our AI is being used inside of third-party systems to solve this kind of problems at a larger scale. So that's our business model, and we're rapidly expanding the business model. So we're going into verticals ourselves, and we're also constantly looking for partners who want to explore new verticals where symbolic AI can be well integrated. So that's the business model.
Great. And is there a fixed pricing, or everything is on demand for the license?
It's on demand.
And there's no way is there any way for like external companies to use the full version of your product, being the license fee, of course?
Yeah.
Or
so if they give us a call, we can give them access.
That's it.
That's nice. I think people out there want to know. And okay.
Yeah. Do you think it would be nice to like share one of the best or one of the use cases that you're proud of that clients use to apply QLattice so far?
Yes. So we have a history in medical research and pharma. That's where, as we were developing the AI algorithm, we needed some interesting problems to work on. And that led us to collaborate with a lot of researchers in life science and pharma. And in life science, medical research, we have this long tail problem that there are diseases that are quite rare. And it's difficult to really get good understanding of the process that causes those diseases. So historically, you can't use machine learning to analyze it, because maybe if you only have, like, say, 25 patients with a certain disease in the entire population that you've studied, there's no real good way to analyze that with sub-symbolic approaches or machine learning. We have many, but I can just give one example where we were able to, in a patient population of just below 20, to actually identify that these patients were suffering from two different diseases. There's like, they had the same phenotype, so it looked like they had the same disease, but ultimately we were able to hypothesize, or the AI was able to hypothesize an explanation that could explain half of them. And then, since the explanation was fairly transparent, we could show that to domain experts who said, aha, That's a eureka moment. If this is true, then that kind of explains why the drug we're working on only works on half the patients. And then they had, there's also always a leap of faith when in medical research, when you go on ahead and try to see if this is true or not. You have to do another study on humans. But it turned out that it was correct. So we have an example where, based on a very, very small population, we were able to accurately identify that there was a real disease process happening in one half of them, and this patient population would benefit a lot from a specific medicine that the other patient population would not benefit from. And that ultimately meant that it was possible, or at least it's in the process of getting approved as a drug that can treat this population group that otherwise would have not been treatable, because now we actually understand the etiology, so now it can actually get approved. So I see a massive potential in those kind of situations where like getting understanding in this case can be life-saving for a population group. And I actually think that there's a revolution of the medical science field coming from applying our approach, where we can gradually like divide and conquer all the rare diseases and get a good understanding of the etiology, as it's called, of those diseases. And yes, it's not the most profitable use case, at least not on the short term, but it's something that makes it worth going to work in the morning. They're actually out there building a technology that is saving lives.
Yeah.
And we have so many examples of that where we've contributed to groundbreaking new understanding of diseases.
Yeah.
But the common denominator is new understanding of something that was not appropriately understood before, whether that is a disease or a reason why a windmill breaks down or whatever it is. In all of these situations, it's new knowledge that you can act on, which is like producing knowledge is one of the things I enjoy most in life.
Yeah. But do you think that because it's something that I'm not familiar with, so does Abzu QLattice work like on demand? Like, for example, if things are happening on the ground, it simultaneously gets the data and does the computation, or it takes some time to process the data? Because, like, for example, some companies would say, oh, they have this machine learning system that gets data simultaneously, and then they try to understand or predict that something will go wrong in a few hours or whatever. What's the time frame for Abzu's QLattice to work?
Yeah, that kind of online training is very feasible. It's not so the rate at which it actually generates new theories or hypotheses is quite fast. So you can be fully online with a model where you essentially be monitoring a constant flow of data from some kind of manufacturing line, and then you could be updating your estimation of what's going to determine the performance of this manufacturing line. But again, it's important to take a step back and say what the QLattice would deliver is not a prediction of when the machinery will break down. It is a best estimate about what determines whether this machinery breaks down. But that can still also be a highly dynamic thing. And that's, for instance, if you're talking about a transport network or something like that, then rerouting a train or shifting a container on a ship can have like dynamic effects on the system that actually require you to relearn the behavior of the system. So being online in this sense is super useful, because you're talking about it, you're studying a system that itself is changing. It's a complex adaptive system. It is feasible, and it is a use case like that in the logistics area. For instance, we've seen that a lot. That to use this to predict like ripple effects in networks. The prediction power is important, but and actually the ability to kind of simplify what's happening in the network is also important, because it allows the operators then to change their decisions about which container to offload, or which train to reroute, or which plane to switch to another gate, or whatever it is that you're trying to optimize for.
So that's reflect a lot. It's a new technology. It's very promising, and I'm actually looking forward to give it a try on the reversion and see what can do. And I think
we go to the last question.
We can move on to the last question.
Okay. So Casper, are you ready? What book would you recommend to our listeners?
So there's a lot of good AI books, but I think that I'm really interested these days in the future of artificial intelligence and its interaction with humanity. Like, where are we heading? We are inventing a technology that is to a large degree going to automate things that was previously done by humans. So we're really changing society in a way that hasn't been seen since the Industrial Revolution. And this time we're automating some of the most valuable work that we humans are doing. That has, over the years, led me to think more and more about what it even means to be human. What is the human condition like? And are we building AIs that are like replacing humans, becoming like humans? Do they have like the same rights and permissions and obligations as humans, or should we be afraid of them? Are we building an alien species that will ultimately kill us all? These are big questions, and I'm a super optimist, but it has led me to be super fascinated by philosophy of mind, actually, and by trying to understand what is it even to be alive and conscious, and when are the machines who build conscience. So the books that I have my head full of these days are about philosophy of mind and in the intersection of artificial intelligence. So if a viewer or listener are interested in kind of diving into what do we know about how the human brain works and what is consciousness and what is it like, and then I think books in that domain is what I would jump on. And I have a specific one that I tend to recommend when people want to understand philosophy of mind, and that's a book by Philip Goff, a British philosopher, called Galileo's Error. And it essentially describes how we get our understanding of the role of consciousness in the universe wrong. And I think he's onto something. And for the AI researcher, it's super important because it also tells us something about when will our AIs actually be conscious, and when will they be true living individuals like ourselves. Will it ever happen? So I won't spoil what he actually ends up concluding, but just say that it's a good book to get a feeling for this. And he also has just released a newer book I haven't read yet. So it's called Why? The Purpose of the Universe. But I can't really formally recommend it because I'm not done yet.
Is it good so far?
Yes, it is. Yes, it is. So if Philip Goff hears this, I'm in doubt about the fine-tuning argument of chapter 1. I find that a little hard to believe. I think you missed the point. Reach out if you want to understand why.
We'll spread the word.
Yeah, we'll have to have a read first, though.
We'll send our PR to Philip Goff. Please listen to this episode. Okay. Thanks a lot for the chat. Really interesting. And I cannot not recommend the community out there to try out this approach, and to business people to try to understand and what are the advantages of this kind of explanatory AI in their business flows. Because
let's say also, if people are saying, "Oh, what is explanatory?" It's also like transparent AI.
Yeah. Also, so there's a lot going on. Thanks you again for being here with us and discussing this new topic. And
if people would like to learn more about our podcast and our guests, they can check out our show notes and hit the subscribe button to receive updates from our podcast.
Thank you, and hope you'll hear from us next time. Bye.
Thank you, Casper.
Thanks for having me. Bye.